welcome back to Everybody Codes 2025. So, for today's problem, we're back on a grid. We have a volcano on this grid whose point is marked with an @ sign, and the remaining tiles are assigned with digits from 1 to 9. The lava flows out from the volcano steadily, and it forms a circle. So this is a true circle. It's not using Manhattan distance or anything. So a point is within a certain radius if the x offset and the y offset are the square sum of that is, the sum of squares of that is less than or equal to the radius squared. So basically using the actual diagonal length between the 2 points. So for example, for radius 6, we get a circle like so. This point is within because if we take the x offset and the y offset and square them and add them up, it'll be less than the radius squared. So given a grid, we want to find the sum of all cells that will be destroyed by the lava. And so the lava spreads out at a radius of 10, so we want to find the sum of the numbers within that range. Okay, so to get the grid, for each line in the input, we will want to go through each character in it. And if the character is an @ sign, we'll mark it with a 0 because that way it won't affect the sum. And otherwise, we will parse it into an integer. So we'll get something like that. Now we want to find the starting position for the volcano. We don't want to assume the grid's always going to be the same size. So for each row and each column, if we see a 0, because the input does specify that the remaining numbers will be from 1 to 9, then we'll say that the ZR and ZC equals RC. I'm using Z here to denote 0. That's just the shorthand that I went with for this. So ZRZC will now tell us where the volcano is. And so now we just need to go through all points that are within the radius. So radius is 10, and for each number in the grid, we'll see if it's in the radius, which we can do by checking if the difference between the row and the volcano point squared plus the column difference squared is less than or equal to the radius squared. If that's the case, then we'll add the number to the total, and finally we can output the total sum. And so that'll get us our answer for part 1. Moving on to part 2, we want to calculate the sum of the cells destroyed during each step times the radius at that step. So basically, we're incrementing the radius by 1 each time and seeing the amount of new destruction. And then we will find the layer that created the greatest destruction on its own, multiply that value by the radius to which the lava increased at that step, and the answer is going to be the product of those two values. Okay, so we'll keep this code around. And now we'll keep track of the maximum. So we'll call it the, let's just call it most for most destruction. It's going to start out as 0 destroyed and radius 0. And then each time we increase the radius, so let's do for radius in range, minimum radius is going to be 1, and the maximum radius is going to be the length of the grid times 2. So that's just an arbitrary value. That's definitely larger than the maximum possible for the grid. At this radius, there are no points within the radius anymore, but that's perfectly fine. Efficiency isn't too much of a concern here. So in the spirit of efficiency not being that much of a concern, we'll just loop through the entire grid on each of these iterations. This is O of n cubed, where n is the size of the grid, but the grid is small, so that's completely fine. Okay, and so to check if something is destroyed at this radius, we need to check that it's not destroyed before it. So recall from earlier that we checked if the sum of squares is less than or equal to the radius squared. So if we subtract 1 from the radius and square it, then our check value should be strictly greater than that. So that'll look something like this. If radius minus 1 squared is strictly less than r minus cr squared plus c minus cc squared, which is less than or equal to the radius squared, then we'll add that to the total. And then we'll say most equals max of most with a pair where the first item is the total and the second item is the radius at which we caused that destruction. So because Python sorts objects lexicographically, it will first compare by the first value, so we'll get the item with the largest total destruction, regardless of the radius. The only time the radius matters is if there's a tie with the total. So finally, we should be able to just take the two values for the total amount of destruction and the radius at which it was the maximum, and taking their product should give us part 2. So let's just test this. That gives us 1090. And that gives us our answer for part 2. You'll notice that it took a second, but it doesn't really matter, so I'm not going to optimize this further. Okay, finally for part 3, we want to create a loop around the volcano to stop the destruction. So we're going to have a specific starting point S, and the lava will increase its radius by 1 every 30 seconds. We immediately begin building a loop, but the numbers represent how much time it takes us to go through each value. So we have to start and end at S, and starting and ending at S takes no additional time. And we have to pay the time cost for every cell every time we pass through it. So even if we pass through a cell twice, we still have to pay the cost twice. We need to be able to create a loop that goes around the entire area of the volcano, but if the lava spills over any part of the loop before we close it, it will destroy the whole loop. That is to say, we need to race the volcano. We need to compromise between not letting the volcano get too large, but also being able to get all the way back to the starting point before the lava hits any part of our loop. So for example, we can't surround the volcano with a radius of 1 because it only takes half a minute for the lava to reach that radius, and we can only just barely get to the volcano by then. Same goes for a radius of 2. You can see on this map that the radius is currently 1, and it takes us 55 seconds to get just barely around the volcano, but then before we can nearly get back to the start, the volcano will expand to radius 2. Radius 3 likewise fails. Radius 4 likewise fails because we now need to go around a wider area. And finally, at radius 5, we see that the volcano is currently at radius 4 and it will take 150 seconds to go to radius 5, but just barely in time, within 148 seconds, we are able to close off the loop and stop the spread of the lava. Okay, so it took me many tries to get this. I had a couple of iterations of an idea. The idea that I ended up going with which I solved this problem, which was unfortunately really inefficient because I didn't think to try a minor optimization that would have actually saved the entire runtime of the program. Basically, my initial thought was to assume that we'd always be at the closest point directly to the left of the volcano, directly below it, and directly to its right. And so the idea was to do a path finding from the start point to the left point, then to the bottom point, then to the right point, then back to the start, and see if that was fast enough. Now, unfortunately, this assumption is not always correct. We won't always necessarily go to that specific point. So the next idea was to try every combination of all of these, and all of these. And that did get me the correct answer, but the program took about 25 minutes to run. An optimization that I found, but unfortunately only after I got the answer already, was if you only try the 10 closest points within this range, then it's fast enough but still gets the correct answer. However, that's an assumption that I don't want to make, because it is possible that there is a chain of particularly low numbers that's outside of that range of 10 values that I arbitrarily chose. So the idea I ended up going with, and I did base this solution ultimately on the idea that Mr. Crop in my Discord server mentioned. So thank you very much to Mr. Crop for the idea. I had a vague idea, something along these lines, but I wasn't ever able to figure it out. Their idea was basically to determine if the path has made a loop using by checking how many times it crosses this line, basically. And so basically what they said was they solved it by requiring that the path has to go right at least once more than it goes left below the volcano. So that's not exactly how I ended up solving it, because I had a bit of trouble getting that work, but it did give me the idea to basically acknowledge the fact that we can use this point here to determine that basically one part of the path needs to be on the left and one part needs to be on the right. So the way I ended up separating left paths from right paths didn't ultimately end up being based on whether or not it passes over the bottom of the volcano, but it was still inspired by what Mr. Crop mentioned. The way I ended up going with it is seeing if the path intersects any of the points to the left of the volcano or any of the spots to the right of the volcano. I found this to make a bit more sense because I was having trouble rationalizing how I would deal with paths crossing over the bottom multiple times. Now with Mr. Crop's solution, if they simply went for one pass around the entire thing, it would have worked fine, but I wasn't quite able to figure that out. The way I ended up doing was basically find the distance to all of these points and then check all of the points that we go to via a left path and all the points we go to via a right path, and eventually we'll be able to find two neighboring cells where one is reached from the left and one is reached from the right, and then we can just add up the lengths of those two paths. Okay, so you may recall from an earlier day that we used something I called flood fill, which was basically doing a breadth first fill, doing a breadth first search, but with no endpoint in mind. Basically, that allowed us to get the distance from the starting position to all points. Because normally when you do a breadth first search, if you keep track of the distance to each point, you'll have that for all points that are found before you find the endpoint. So if you simply don't stop until you've exhausted the entire grid, then that'll give you the distance to every point. Now, because the weights are uneven, because the cost to step to each cell is not always going to be the same, we can't use breadth first search here. A couple days ago, I think it was, I used Dijkstra's algorithm, which is a way using priority queues to find the shortest path on a weighted graph. We're going to do the same thing here and simply not have an endpoint. So the original Dijkstra's algorithm is actually to solve the single source shortest path problem, which is basically given a graph and a single starting point, find the shortest path to all nodes. So when we use Dijkstra's algorithm to search for a specific endpoint, that's actually a specification of it. So here we're going to implement the original of it, basically. Okay. So we're going to need to add an extra condition here. If the starting character is S, then we'll make it a 0, because this won't interfere with the pathfinding, because the cost to go back to the starting position is 0, as mentioned in the problem. I chose to use -1 to represent parts of the map that will have been destroyed. You can choose to use something else like none, for example. I just found -1 to be easier. So we'll make the volcano itself -1 because we can never step onto the volcano. Okay. And so now we'll also need to find the starting point. So 0 now represents the starting point, and -1 now represents the volcano, which I've called ZR for some reason. I guess VR and VC would make more sense. And now we need to find the radius at which we can close a loop. So let's just do the same iteration as before. We'll set... we need to be careful with the one-off here. I chose to use radius to represent the radius that the volcano is currently at when we close the loop. That is to say, the amount of time we have is actually going to be radius plus 1 times 30, because we have as much time as it takes the volcano to get to the next radius up. So we'll initialize the radius at 0, which is the starting point, so that gives us 30 seconds. And we'll still iterate up to this point. But we'll never reach that anyway, so it's fine. And so each time I will modify the grid by destroying all of the items within this radius. So for R in range length grid, for C in range length row, if this is in range, then I will do grid RC equals -1. So each time I'll set all of the values within the lava radius to -1. And this is the current radius that's already been destroyed. So this will be accurate with starting the radius at 0. So now let's do our Dijkstra's algorithm. And so for that we'll need a priority queue. So I'm not going to go over priority queues again. I don't quite remember which video it was in, but I'll try to remember to link it back. It should be in the top right corner if I remember how YouTube works. Okay. So we'll need to keep track of which points we've seen. And this time, instead of using a set, I'll use a map. And that's because we want to remember first what the distance is to each point from our starting position, and second, also how we got there. We need to trace back the paths because we need to identify which point was reached from the left and which point was reached from the right. So we will keep track of both the distance to a point and the point that we were at right before we got to that point. Basically, we're keeping track of a way to backtrack from each point, and this will allow us to construct the paths later. You'll see how this works once we get to that point. Storing the path within each state is too inefficient. And then we'll have a priority queue, which will be 4 values: the time, the current row, the current column, and our last position. Okay, so if we've already seen this value, we will skip processing it. Otherwise, we'll add it to the scene map with the distance, or rather the time it takes to get there, as time, and the last position as last. And now we'll go through each of the neighboring cells. So for each NRNC in those, we have a couple things to check. So if it's already been seen, then we'll skip it. If it's out of bounds, then we'll also skip it. And if it will take too long to get there, so if the current time taken plus the amount of time it takes to step onto that is greater than the amount of time we have left, which, as a reminder, is radius plus 1 times 30, because we have until the volcano reaches the next layer, we'll skip it. And, oh yeah, also if that point is -1, that means it's already been touched by the lava, so we can't go there. So if it's -1, then we'll skip it. Finally, if all of these are true, then we'll add it to the priority queue. So heap q.heap push pq. The new time is time plus grid nr and c. The new row and column are nr and nc, and the last position is where we currently are. Okay. So now we have a record of from each point to where we got to it. So if we were to try to store the whole path that we took to get to each point, that would be too inefficient. So rather what we have here is basically for each point we kept track of where we got to it from. And so imagine we have something like this. This node doesn't know what the whole path to get to it was, but it knows that we got there from this node. And so when we want to go backtrack and check the path, we say, okay, we start here. We look at the node that came before it, that is in the path as well. We look at the node before that, that's in the path as well. Look for the node before that, and that's the starting point, so that is our path. So we can reconstruct the path for any node without needing to store the whole path. I believe this is part of Dijkstra's algorithm itself, because again, the point of it is to construct the shortest path. We usually just ignore that part for path finding. Okay, so let's define a function to check, and this is inside the loop because we're relying on the scene set here. So given a key, which is going to be a row and column pair, we want to figure out if this path is on the left. So if the key is not in scene for whatever reason, which usually will be, I think it'll only be caused by key being none, we'll return none. So this function will return true if the path to the key is on the left, as in it's intersected the line going left from the volcano. That's when it will be true, and it will be false if it intersects this line. But if it intersects neither, that means that the path never went to the below the volcano. So we want to return none to identify that it's not a valid path, and the reason for that is because we want to avoid constructing a loop that sits entirely above the volcano. Forcing one path to go left and one path to go right will allow us to guarantee that the volcano will actually be surrounded. Now technically I think it's possible for us to have some... no, it's not possible. Right, because... Okay, basically, in the end we'll be looking for two adjacent points where we reached one of them from the left and one of them from the right. And barring weird edge cases, that basically guarantees that one of those... that the paths added up have to go around the volcano. Okay, so if the key is in scene, then we know it's not none, so it has to be a pair. So RC equals key. If the row of this node is equal to the row that the volcano is in, then we'll return C less than ZC. And what this does is, if C is less than ZC, it means that the column of this point in the path is to the left of the volcano, so we return true. If it's to the right, then we'll return false. Otherwise, if neither of these are the case, then it tells us that this is a node on a path, but we don't know if it's to the right or the left, so we'll backtrack. So underscore last equals scene key, because the first stored value is the distance, and we're just checking the path direction, so we don't care about the distance here. And we'll recursively return whether or not the last point was to the left. Basically, given an end position here, we'll recursively backtrack along the path until we either get to a point that's on the left or on the right of the volcano, in which case we get true or false, or if we make it all the way back to the starting position without ever crossing the volcano row, that means that the path is entirely above the volcano, so we can ignore it. Finally, because we're doing a lot of recursing here, I'll just tag this with a functools.cache to memorize it. So basically this just avoids duplicate computations. If a cached function sees the same key passed into it, which will happen a lot because of this recursion, then it will just return the value from cache and avoids needing to run the whole recursion again. Okay, finally, let's keep track of which nodes were reached from the left and which were from the right. So the left ones will be key for key in scene if is left is true. And so we check if it's equal to true here because, well, I guess in this case, that part technically doesn't matter. What matters here is that if we do this, then this will also hit all of the keys with a path direction of none, which we specifically do not want to include. So instead of doing not, we'll check if is left is strictly equal to false, which will only be returned if we see the path cross the volcano row on the right side. Okay, and finally we want to keep track of the best possible path. So we'll start that off at infinity, basically representing impossible. And finally, let's say for LRLC in all of the left nodes, the possible right, we want to look for right nodes that are adjacent to it. So for RRRC in the neighbors, if it was reached from the right, I guess we don't need this in that case. If it was reached from the right, you know, I guess I don't need this either. Okay, if not is left key, or LRLC, continue. Yeah, since we're memorizing, we don't need to be efficient with saving function calls. Okay, so basically for each of the nodes that we can reach, if it's not a left path, then we skip it. And then otherwise for each of its neighbors, if it's not a right path, then we'll skip it. And otherwise, we'll let best equal the minimum, since we're trying to find the shortest path, between best and the sum of the lengths. So that's going to be scene LRLC index 0 plus scene RRRC index 0. And so that should give us the shortest path. Let's print some out to test. Okay. So it tells us at radius 0 it's impossible. At radius 1 it will take I don't know why radius 0 is saying infinite, but that's probably not a concern. Radius 1 it will take 88 seconds, which is too slow. We need to do it within 60. Radius 2 will take 107 seconds, which is too slow. We need it within 90. Radius 3 will take 134 seconds, which is too slow because we need it within 120. And finally, radius 4 is the first one at which we can contain the radius, at which we can contain the lava in 148 seconds with 2 seconds to spare before the radius becomes 5. Okay, so finally, the amount of time we have is radius plus 1 times 30. So if the best score is less than or equal to, I guess strictly less than, because we can't allow the lava to touch the, I don't know which way the one-off goes. I think it's less than or equal to here. If the best value is less than or equal to the amount of time we have, then we want to print the amount of time it takes times the radius at which we can contain it, which is the answer we're supposed to provide for this part, and we'll exit the loop once we found our answer. So that gives us 592 for the first part. $330 for our second test case. So that is not the correct answer for the third test case. So let's go add the debug back in. Okay, so it's telling us that we can contain it at radius 9, which does seem to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we're not supposed to be able to contain it within 10. Yes, sorry, it is supposed to be strictly less than here. Okay, so it is supposed to be strictly less than, because I guess the last step still, basically, if the lava spreads at the same tick that we reach the second to last square right before we go to the start point, even though going back to the start point takes no extra time, it'll still destroy it. So this will give us our correct answer. Okay. And so, although we can't really look at this grid too easily, interesting. Okay, so there's a large block of 9s straight through the middle of the grid right below the volcano. I imagine that's there to mess up some solution, but I guess I didn't even see the solution that would get messed up by it. Okay. I think there's some pattern in this grid. Maybe there's something that we're supposed to be able to visualize, because I think I'm seeing patterns here. Okay. In any case, that's not relevant. Let's run this on our final input. We'll see. It will take a bit of time, but nothing at all compared to the 25 minutes that I spent waiting for my brute forcer to finish. And so that will give us our answer for part 3. So certainly not one of my better performances, but ultimately I did end up getting the correct answer, even if it took almost half an hour of runtime. But fortunately I was able to figure out a better solution for the video, because I would hate to present a really inefficient brute force solution. In any case, that's all for this video. Thank you very much for watching, and I'll see you tomorrow.